Hello everyone, this is Suhail Manzoor from Optimized Solutions LLC. I'm very excited to introduce a software product that is developed and marketed by my company as a toolkit to design and optimize engine mounting systems. The name of the software program is Raptor, RAPTOR, which is an acronym for Recursive Algorithm for Parametric Tracking of Resonance. In this short video, I'll be demonstrating how to input the values of an inertia tensor into Raptor. First, a bit about Raptor. This is a Windows-based program that can be operated from a basic laptop or desktop computer. It can be purchased from Optimized Solutions directly. And if there is interest to procure Raptor, please feel free to email me at the following address, manzoor@opsollc.com. You may also want to visit the company website at the following URL, www.opsollc.com. It is essential to know the full definition of an inertia tensor before performing a calculation. This information is generally received from the engine manufacturer. The inertia tensors are usually defined in two ways. First, when the complete inertia tensor is defined by the engine manufacturer, meaning the main diagonal terms, the Ixx, Iyy, Izz, plus the off-diagonal terms such as the Iyx, Izx, and Izy. Obviously, the rest of the terms such as the Ixy, Ixz, and the Iyz are not necessary to be defined because they are the mirrors of these off-diagonal terms that I just spoke about. So really with 6 terms, you can completely define an inertia tensor, the main diagonal terms plus the off-diagonal terms. When this entire inertia tensor is defined by the engine manufacturer, life becomes fairly easy because that can be fed into Raptor and the calculation can be performed directly. However, there are times when the entire inertia tensor is in fact not provided by the engine manufacturer. What is provided are the main diagonal terms, the Ixx, Iyy, and Izz terms, along with what we call a direction cosine matrix. Now, when this happens, then the calculation becomes a little tricky because that information cannot be directly input into the software by this method. What we have here is under Tools, we have a special toolkit called the Direction Cosine Matrix toolkit, where we can define a full inertia tensor based upon the main diagonal terms and a direction cosine matrix. So let us do that and take this example and actually perform a calculation. So Ixx, I'm going to enter 32, Iyy is going to be 26, and Izz is going to be 28. Now, suppose the engine manufacturer, instead of providing us the Iyx and Izx and Izy terms, has provided us with a direction cosine matrix. That direction cosine matrix is now entered in this region here. When you start out, there are a couple of interesting things about a direction cosine matrix that I should point out. The first is that every direction cosine matrix has a unique characteristic. The sum of the squared terms of a column of direction cosine matrix. So 1 squared plus 0 squared plus 0 squared should equal to 1. 0 squared plus 1 squared plus 0 squared should equal to 1, so on and so forth. So every column, the sum of the squared terms of each column should equal to 1. So a direction cosine matrix cannot have random numbers in there. I will actually put in a real direction cosine matrix. The first term is 0.972, negative 0.038, .233, .061, negative 0.994, 0.092, 0.228, 0.104, and 0.968. Once we enter the direction cosine matrix, it's important to understand that we need to verify whether this is a real direction cosine matrix and actually it satisfies the requirement of the sum of the squared terms in each column should equal to 1. In order to do that, we have got a tolerance parameter because these numbers that we see are truncated to 3 places of decimal and there are approximations involved here. So the first thing we need to do is we need to click on this button called Verify Direction Cosine Matrix, and you can see the direction cosine matrix is verified. The sum of the squared terms in each column is indeed equal to 1. This is an important step because sometimes the direction cosine matrix that you may receive from the engine manufacturer may not be an accurate matrix, or there may be mistakes in the matrix itself. So it's very important to do this quick check. And once this check is completed, then you can solve for the complete inertia tensor. Once we click on that, you can see this table here gets populated. You can see the complete inertia tensor gets defined. I will point out a couple of interesting facts here. The first one is look at the main diagonal terms, which were 32, 26, and 28, now are 31.7, 26.03, and 28.20. So the main diagonal terms have slightly changed, and this is an expected outcome. This is what happens when you use a main diagonal term incomplete inertia tensor along with a direction cosine matrix. But also notice how these terms, the IYX is a mirror of the IXY, 0.269, 0.269. Same thing, the IXZ is a mirror of the IZX, negative 0.917. However, look at this IZY term. It is 0.148 versus the IYZ term is 0.147. Now, there is a slight discrepancy then that is because of the approximate structure of this direction cosine matrix, which allows a slight anomaly. However, when you hit this button, export complete inertia tensor, and export it to your main calculation screen, you will see that now the terms are appropriately mirrored and you don't have that anomaly anymore. So that this error that is caused by the approximate direction cosine matrix doesn't get pushed into the entire calculation. You can see now we have perfectly mirrored off diagonal terms along with the main diagonal term, and this can now be used for our calculation moving forward. Hopefully this has given you some insight on how to use the direction cosine matrix tool in order to take the main diagonal terms along with the direction cosine matrix and convert it into a full inertia tensor, which can then be fed into the software for calculating further. Thank you.